Hello, this is a follow-up tutorial to my last tutorial where I explained how you can create this waveform mesh by accessing the real-time audio data from your microphone using Python. And in this video I want to talk about how you can now get this data inside of geometry nodes to use it freely and do whatever manipulations you want. Specifically, I will be explaining this ball example where I'm using the waveform data to just displace it along the normal, and I'm also mapping the waveform based on a grayscale texture. So it's not just linear and we have a little bit more artistic control. Let's get started by looking at the sample index node. As you can see, I have a little test setup here, just using an icosphere base mesh and then offsetting the position by the output of the sample index node. Looking at the sample index node, you can see we have three inputs, the first one being the geometry. So I just input the geometry of our waveform mesh. Then we have a value and the index. So since I set it to vector and point, it will, if I put any value here, so now it's 21, it will take point 21 from this mesh and then sample a vector value. But as you can see, it's not doing anything yet because we also need to connect this value input with the value that we want to sample. So I want to know the position at this index, so I need to connect the position. It's a little bit counterintuitive, at least to me, but now you can see it works. And as I scroll along the indices, the sphere just moves along the wave exactly. Yet to sample this continuously, let me just quickly swap out our mesh, our sphere, for mesh line. And let's make it horizontal instead of vertical. Okay, nice. And the second thing I want to change is for the index, I want to actually use the index of our generated mesh. So now when I just decrease the offset a little bit more and increase the count, you can see it's basically, maybe just move it. Oh, maybe let's set it to original. And let me just move it a little bit. Yeah, now you can see it's basically creating a copy of the waveform mesh because we are inputting the index into the index, meaning point 1 of our generated mesh will sample the position of point 1 of the original mesh and then just set that position as the offset. And as you can see, if I go above the number of vertices, so I know that we have 2048 vertices in the original mesh. And if I exceed this number, then it stops working, obviously, because it says that I want to sample point 2050, but it doesn't exist, so it fails. What we can do to get around this is use the map range node in combination with the domain size node. So what the domain size node lets us do is we can just input any geometry. I will be inputting our original mesh, and then we can get the number of any type of mesh object. So for example, points, So it will just give us the number of points in this mesh that we input. And the map range node, if you are not familiar, it basically allows us to scale an input value. So in this case, we know we will be getting from this index, because this is the generated mesh, we will be getting numbers between 0 and 2050, because we have 2050 points. Actually, it would be 2049 because it starts at 0, but same difference. So this will be our value range, 0 to 2049. And then we could say, oh, okay, this is our maximum. So getting the point count from here. This is our maximum input. And let me just copy the index. So inputting the index, we know this is the maximum the index can be. We know 0 is the minimum it can be. But now we want to output it rescaled to a range from 0 to 1. So putting it like this, basically index 2049 will now be 1 instead of 2049. And a value of around 1000 would be 0.5. So this is how mapping ranges works. Let's do something with it here. So I want to account for the difference in points between our two meshes. The way to do this is, so we know for the output, so our maximum index value that we want to sample will be the number of points in the original mesh. So let's connect this here, and this will be the output maximum. And the maximum input will be the number of points in our generated mesh. So let's copy domain size, make a little bit of space here, and connect this to from maximum. And since we are getting the index here, if we now put this into the index, you can see firstly the error disappeared, but also if I change the number of points, we basically always get pretty much the same result. It just squishes and stretches a little bit. And the reason for this is that now we are remapping the number of points. So now we have 358 as our maximum, and this says, oh, if I get this number of 358, it should be the maximum value, and it scales it to this to maximum, which is then the number of points in the original waveform mesh, and we know it's 2048. So inputting, if the index is inputting 358, it will be outputting 2048, and this is what then the sample index node is sampling from the waveform mesh. So yeah, it just accounts for the difference in points, but of course resolution will suffer. So you can see if I go really low, now it doesn't have enough points to represent the shape. It's doing its best. Okay, playing around with it a little bit, I noticed that of course directly putting the position value into the offset is not optimal, because then we will also be getting the offset in the x direction and in the depth. I mean, there is no depth data to be used here, but in theory. So quick fix for this is just using a vector math node and then multiplying it component-wise by 0, 0 and 1, 1 being then the z-axis, so the height. So we ignore every position value except the vertical offset. And this is also why I needed to make the offset of the mesh line so small, because then it added the offset that we were getting from our original wave mesh. Okay, so what I did here is I just remapped first the our value range, so we get the generated mesh, and we say, oh, it can have this many points using the domain size node, and then I say, okay, please give this to me in a 0 to 1 range. And what this allows me to do is then use the the color ramp node, because now we have a grayscale, and now I can like move it around, and even I could add a point in the middle, and it's like stretching on one side and squishing on the other side, or we could just like flip it around, or I can add another point on the other side, and then it's like mirrored from this black point. And after I'm then manipulating, or after I manipulated the grayscale, then I'm just mapping it again from 0 to 1, then to the maximum number of points that we have inside the waveform mesh. So this being the original waveform mesh, not the generated one. And yeah, I guess you can already see how we now have this data very usable. So with all of these concepts in mind, let's build one other node setup from scratch. I just kept some nodes here that we will definitely be using. So just sampling the index using position value from our waveform mesh, and then multiplying the output so we isolate the z value. Firstly, I want to change out the mesh line for a plane. Let's go 2D. Nice. And now what I want to do is map this waveform data based on a gradient texture. So gradient texture, nice. Yeah, how can we do this? So we know we get some grayscale value here from the factor, and we know we can sample, the highest index we can sample is 2048, which we get from the domain size. So let's start with this. Let's get the domain size and use it again with the map range. Where is it? There we have the map range. So this will be, the point count will be our output maximum. The gradient texture will be our value. It's from 0 to 1. This is already correct, so we just leave it. And then we feed this into the index. So we have to change a few things so we can actually see something. First, I just increase the number of vertices. Okay, we can already see something happening. So this looks like the start of our wave here. And maybe I actually want to use not a linear gradient, but a spherical one. Nice. Already some 2D action. And let's scale it a little bit. So we do this by just using the position, because position is the default vector that textures are using to map in geometry nodes. And so okay, we connected, nothing changes because it was already doing this under the hood. And now we are using vector math and just scale. And now if we change this value to something other than 1, you can see here we have the full data just mapped nicely onto our plane based on a texture gradient. And now what we can do is just swap out this boring gradient texture, for example, for a noise texture. Okay, it looks very messy because it has many gradients. So we showed the whole waveform many times on our small mesh surface. So let's decrease the scale and very slowly. Now you can see we have some very interesting patterns emerge here. Let me just decrease the resolution again. And now you can see it's still the real-time data. It's actually mapping what's happening in my microphone to this plane and then distorting it based on this crazy noise texture. If I pause here quickly, nice, I caught a moment where there was something happening, and maybe increase the resolution to something crazy. Now you can see there's some artifacts happening. We have some staircasing, and this is happening because the density of how we map our data compared to the mesh density is not even across the whole surface. So we might, in our noise texture, we might have a small blob where the gradient falls off very quickly. And in other points, we might have like a very big gradient. I can show this off even more, maybe if I put it to, if I put the scale to something. Okay, it was too small. Let's see. Yes. Now you can see we have a lot of staircases here. Just because now we are spreading out a small amount of waveform data across a very big area and across many points in our mesh. So how can we get around this? The secret word is interpolation. So because from the map range, the output, as you can see here, is actually a float. But the index is an integer, so it can just take full numbers, because we cannot have vertex number 500.2, because it's, we only have 0.500 and 0.501 and not any in-betweens. So what I did to prevent this is I just sampled the index twice. Let's do this. So all the same inputs, same geometry, but the output of the map range node, we use a math node. And one time we floor it. What this does, it just says if the value is 500.2, it will be 500. So it just removes the fraction, the fractional part, whatever it is. And then for the second one, we will be sealing it. And this is the opposite. So the value 500.2 will be 501. So it always rounds up, no matter how small the fractional part is. So this setup says if we have an in-between value, it will get the number below it, like the full number below it, and the full number above it. And now we can mix it. Let's specify that's a vector. And mix it and just put it into our multiply node. And you can see not much has changed, like everything shifted just by a pixel. And if I slide this around, this is what's happening. And now the key is we want to mix those two values based on the fractional part of our original. Doesn't work like this. Let's copy the math node. We want to mix based on the fractional part of our original input. So let's get the fraction here, yes, and use the output of our map range. So here we are getting, again with the example 500.2, the fraction output will just be 0.2. So if I now move this over here, we'll be mixing based on 0.2, and you can already see suddenly it's smooth, because for all of the in-between values that were just sampling one or the other, now they're mixing and just blending smoothly between the two values around them. Yeah, and I cannot play it in real time with this high resolution, but we can go down again, and now, yeah, it's just pure amazingness. Finally, let's transfer this to the sphere. We need to do only a few little changes. So if I input the icosphere here, and maybe increase the resolution so we see some displacement. Okay, so it looks like it's working, but let me pause it quickly. If I increase it a little bit more now, you can see it's kind of working, but it's not pushing, like it's not inflating the mesh, it's just pushing vertically, so we don't get any horizontal displacement. The way around this is pretty simple. We want to push the vertices along the normal. So we just get the normal node, and then if we put this into the offset, you can already see it just blows up the sphere. And let me just copy this vector math node and set it to scale. And now if we scale this normal input, you can see we can control how much it is inflated or deflated. And finally, we just want to drive this scale value by a variable, which will be the Z position that we get from the waveform. So our trick with the multiply component-wise will not work anymore. We actually need to separate the X, Y, Z coordinates. And then we can get a single float for the Z position and put it here. Yeah, and that's it. You can see it's a little bit slow. I noticed, like for the intro, I used a pre-made mesh that was not generated inside geometry nodes. Maybe I can show it quickly. Yes, it even says sphere front only. So yeah, first the mesh is just the actual group input and the very dense icosphere mesh, but also I cut off half of it because yeah, the camera view doesn't see the back. And now, yeah, you can see we have amazing resolution, but still it runs quite smoothly. And yeah, I guess that's all. Next, I want to look a little bit, so for the next video, I want to look a little bit at how we can get audio files, so like wave files, which is advantageous for doing offline rendering because this is only real time and you cannot really bake it or render it out with very high fidelity or using cycles. And from there, I think it is cool to combine it with Fourier transform. So then we can do some like pitch detection, instrument detection, and yeah, because I guess just inputting the waveform, it's very jumpy because we are in no way synchronized with the frequency that's going through. I guess, yeah, we're using some pitch sensitive way to manipulate the mesh will give us nicer results. Yeah, so thank you very much for watching. I hope you learned something that was interesting for you, and maybe I can see you again in the next video. Or I guess maybe you can see me again in the next video.